What if I told you there's a world where a cat can be both alive and dead at the same time? Not in some twisted fairy tale, but right here in the fabric of reality itself. This is the bizarre riddle of Schrödinger's cat, a paradox that exposes just how little we truly understand about the universe. And here's the wild part: this isn't science fiction. It's the cutting edge of quantum mechanics, where particles vanish and reappear, where objects exist in multiple places at once, and where the very act of looking at something can change its nature. The deeper we dig into the quantum realm, the more it feels like we're piecing together clues to a cosmic mystery, one that might rewrite everything we thought we knew about time, space, and existence itself. Think about this: every single law of physics that feels solid and predictable in our everyday lives starts to unravel when we zoom in to the smallest scales. Light behaves like a wave and a particle simultaneously. Particles communicate instantly across vast distances, as if space and time don't apply to them. Even the concept of reality becomes slippery. What we observe isn't just a fixed truth, but one possibility among countless others. These aren't just quirks of science, they're screaming hints that the universe operates by rules far stranger than our intuition can grasp. And the most thrilling part: these mysteries aren't dead ends. They're gateways, points where science brushes against something profound, something that could explain why the cosmos looks and behaves the way it does. That's exactly what we're diving into today: 30 quantum mysteries so perplexing, so awe-inspiring, they might just hold the keys to unlocking the universe's deepest secrets. From particles that remember their past to black holes that might be gateways to other dimensions, we're about to explore phenomena that blur the line between science and philosophy. But here's the best part: you don't need a physics degree to come along for the ride, because at its core, this isn't just about equations or lab experiments. It's about confronting the breathtaking strangeness of reality itself. So buckle up. By the time we're done, you'll never look at the world the same way again. One of the most mind-bending revelations in quantum mechanics is that the building blocks of reality refuse to behave like neat little balls of matter. Take light, for example. Fire a beam at a wall with 2 slits and something extraordinary happens. If light were purely particles, you'd expect 2 tidy stripes on the wall behind the slits, just like bullets passing through narrow openings. But that's not what happens. Instead, you get an interference pattern, a series of bright and dark bands, as if waves of light are crashing into each other, amplifying and cancelling out like ripples in a pond. This is the famous double-slit experiment, and here's where it gets weirder. Even when you shoot single particles of light photons, one at a time, the interference pattern still appears. It's as if each photon is passing through both slits simultaneously, interfering with itself. Now, imagine doing this with electrons, tiny particles of matter. The same thing happens. They act like waves, creating that telltale interference pattern. But the moment you try to peek to measure which slit the electron actually goes through, the wave behavior vanishes. The interference pattern disappears, leaving just 2 clumps of particles. It's as if the electron knows it's being watched and changes its behavior on the spot. This is wave-particle duality in action, and it shatters our classical intuition. Particles aren't just tiny marbles, they exist in a ghostly superposition, spread out like waves until forced to pick a side by observation. What does this mean for reality? It suggests that at the fundamental level, things don't have definite properties until we measure them. A photon isn't a wave or a particle, it's both, and neither until an observer steps in. Some interpretations say reality itself is undefined until interaction locks it into place. Others argue that every possible outcome exists simultaneously in parallel worlds. Whatever the explanation, one thing is clear: the universe doesn't play by the rules we grew up with. This bizarre behavior isn't just a quirk, it's the foundation of quantum mechanics, shaping everything from the lasers in your DVD player to the inner workings of atoms. And it all started with a simple experiment that proved reality is far stranger than we ever imagined. If the double-slit experiment blew your mind, buckle up because things are about to get even stranger. Imagine flipping a coin, but here's the catch. Until someone looks at it, the coin isn't just heads or tails, it's both at once. This is the essence of the observer effect, one of quantum mechanics' most baffling revelations. At the quantum level, particles exist in a haze of possibilities, and the simple act of measuring them forces reality to make a choice. It's as if the universe hesitates until the last possible moment, then snaps into focus under our gaze. Take the classic thought experiment dreamed up by physicist Eugene Wigner. Picture a scientist in a lab measuring a quantum system, say an electron spin. According to quantum rules, the electron exists in all possible states simultaneously until measured. But here's the twist. Wigner imagines a second scientist outside the lab, unaware of the first's results. To this outsider, the entire lab, including the first scientist, remains in a superposition, unresolved. So who's right? When does reality actually happen? The unsettling answer: it depends on who's looking. This paradox forces us to confront a dizzying question: what counts as observation? The Copenhagen interpretation, championed by Niels Bohr, argues that measurement collapses quantum possibilities into concrete outcomes. But it doesn't define what constitutes a measurement: a human eye, a camera, a single atom bumping into another. Some theorists suggest consciousness itself plays a role, while others propose that every possible outcome branches into parallel universes, as the many worlds interpretation suggests. The implications ripple far beyond thought experiments. Quantum computers exploit this very principle, harnessing particles in superposition to perform calculations at unimaginable speeds. Yet, even as we engineer technologies around these rules, the central mystery remains: why does observation hold such power? Is reality a cosmic game of hide and seek, only revealing itself when demanded? Or are we glimpsing something even deeper, a universe where participation, not passive observation, shapes the fabric of existence? One thing's certain: in the quantum realm, the line between witness and creator blurs beyond recognition. If quantum superposition left you questioning reality, entanglement will make you rethink the very nature of connection itself. Picture two particles born from the same quantum event, maybe electrons spinning in opposite directions or photons polarized at matching angles. Now fling them to opposite ends of the galaxy. According to the rules of quantum mechanics, measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, dismissing it as impossible because it seemed to violate his theory of relativity, which states nothing can travel faster than light. Yet decades of experiments have proven entanglement isn't just real, it's one of the universe's most fundamental features. The breakthrough came with physicist John Stuart Bell's theorem in the 1960s. Bell devised a mathematical way to test whether entanglement's correlations could be explained by hidden variables, secret instructions particles might carry at birth, like cosmic cheat sheets. But when scientists ran the experiments, the results were unambiguous. No hidden variables could explain the instantaneous connection. Particles really were influencing each other faster than light could travel between them, as if space and time were mere illusions to them. This isn't just theoretical wizardry. Entanglement powers emerging technologies like quantum cryptography, where particles serve as unhackable messengers. Intercepting a message would collapse their quantum states, alerting users to eavesdroppers. Quantum computers, too, rely on entangled qubits to perform calculations that would take conventional machines millennia. But the implications go far beyond engineering. If entangled particles ignored distance, could the universe be fundamentally interconnected in ways we've yet to grasp? Some theories suggest entanglement might even underpin space-time itself, weaving the cosmic fabric from invisible quantum threads. Yet the biggest mystery remains unanswered. How do entangled particles communicate? The math describes the effect, not the mechanism. Maybe information tunnels through hidden dimensions. Maybe every particle in the universe is subtly linked in a vast, unseen network. Or perhaps, as some radical theories propose, separation itself is an illusion, a trick of perception in a holographic cosmos. Whatever the truth, entanglement forces us to confront a universe far more intimate, more mysterious than Einstein ever imagined. And we're just beginning to unravel its secrets. Schrödinger's cat isn't just a thought experiment, it's a window into one of quantum mechanics' most unsettling truths. Picture a cat sealed in a box with a vial of poison, rigged to break if a radioactive atom decays. According to quantum rules, until you open the box, that atom exists in a superposition, both decayed and not decayed at the same time. So by extension, the cat is simultaneously alive and dead. Absurd, right? Yet this paradox captures the essence of quantum superposition. Particles don't settle on a single state until forced to by observation. This isn't just theoretical wordplay. Superposition is the engine behind quantum computing. While classical computers rely on bits, zeros or ones, quantum bits or qubits exploit superposition to be 0 and 1 simultaneously. It's like flipping a coin mid-air, neither heads nor tails, but a fluid blend of both. This lets quantum computers explore countless possibilities at once, solving problems in minutes that would take conventional machines centuries. Take cryptography. A quantum machine could crack codes by testing every possible key concurrently, a feat impossible for binary logic. But superposition isn't just about processing power, it rattles the foundations of determinism, the idea that the universe unfolds along predictable cause and effect chains. If particles lack definite states until measured, does reality truly exist independently of observation? The Copenhagen interpretation says no. Reality coalesces only when probed, like a dream solidifying under scrutiny. But alternatives like pilot wave theory argue hidden forces guide particles, preserving determinism beneath the quantum haze. Here's the kicker. Even if determinism survives, superposition forces us to grapple with a universe far weirder than Newton ever imagined. A universe where particles dance in probabilistic shadows until pinned down, where possibility itself is a tangible ingredient of reality. Whether you see this as a glitch in existence or a clue to its true nature, one thing's certain: the quantum world refuses to play by the rules we've written for it. And the closer we look, the more we realize those rules might just be illusions. The measurement problem is quantum mechanics' elephant in the room, a glaring mystery that even the greatest minds can't fully explain. Picture rolling a die, but until you peek at the result, it's spinning in a fog of possibility, showing all 6 numbers at once. That's how quantum systems behave, existing in multiple states until measured. But here's the million-dollar question: what is measurement, and why does it force reality to pick a side? Start with the Copenhagen interpretation, the old god of quantum theory. It says measurement collapses the wave function, the mathematical cloud of probabilities, into a single outcome, but it's oddly silent on what actually counts as a measurement. Is it a conscious observer, a lab instrument, a stray photon bouncing off the system? This vagueness has fueled debates for decades. Take Wigner's friend, a twist on the classic thought experiment. If a scientist measures a quantum system, it collapses for them, but to another observer outside the lab, the entire setup, including the first scientist, remains in limbo. So whose observation counts? Enter the many worlds interpretation, a radical alternative. Here, there's no collapse at all. Instead, every possible outcome splits the universe into branching timelines. In one world, the die lands on 3, in another, it's 5, no dice are left unrolled. It's an elegant way to dodge the measurement problem, but it comes with cosmic baggage, an infinitude of parallel realities, each playing out every quantum possibility. Then there's pilot wave theory, a quieter but persistent contender. It suggests particles do have definite positions guided by hidden pilot waves that orchestrate their behavior. No collapse needed, just an unseen hand steering the quantum dance. It's deterministic, almost nostalgic for Newton's clockwork universe, but at the cost of ghostly influences lurking beneath reality's surface. Objective collapse models take a different tack. They propose wave functions collapse spontaneously, not because of observers, but due to tiny, inherent instabilities in the fabric of reality. It's like a soap bubble popping on its own, no finger needed. Experiments are hunting for signs of this spontaneous collapse, but so far it's still speculation. Why does this matter? Because the measurement problem isn't just philosophy. It cuts to the heart of what reality is. If observation shapes existence, does the universe need conscious beings to give it meaning? If branching worlds are real, where does that leave our sense of uniqueness? And if hidden variables or spontaneous collapses explain it all, what other shadows lurk in quantum theory's blind spots? The unsettling truth is, we still don't know why measurement has this power. It's the seam where quantum weirdness meets everyday reality, and the stitches holding them together remain invisible. Until we unravel this mystery, the universe keeps its deepest secrets close, revealing just enough to remind us how much we've yet to understand. Imagine throwing a ball at a wall, only to watch it suddenly appear on the other side without breaking through. In our everyday world, that's impossible, but in the quantum realm, particles pull off this exact magic trick. It's called quantum tunneling, and it defies every classical law of physics. Here's how it works. At the subatomic level, particles don't behave like solid objects, but as waves of probability. When they encounter a barrier, like an energy wall that, according to Newtonian physics, should stop them dead, there's a chance they'll simply tunnel straight through, as if the barrier were a fleeting shadow rather than a solid obstacle. This isn't just a theoretical oddity. Quantum tunneling is the reason the sun shines. Inside stars like ours, hydrogen nuclei repel each other due to their positive charges. Classically, they'd never get close enough to fuse and release energy. But thanks to tunneling, there's a tiny probability these nuclei will bypass the electrostatic barrier entirely, allowing fusion to ignite the stellar furnaces that light the cosmos. Without tunneling, stars, and by extension, life itself wouldn't exist. Closer to home, tunneling powers the devices in your pocket. Modern electronics rely on transistors, the tiny switches that form the backbone of computer chips. At nanometer scales, electrons tunnel through insulating layers, a phenomenon engineers once saw as a nuisance but now harness to design faster, more efficient processors. Tunnel diodes, for instance, exploit this effect for ultra-high-speed applications, while flash memory uses tunneling to store data by precisely shuttling electrons across barriers. Even your body plays the tunneling game. Enzymes in your cells use it to accelerate chemical reactions, making life's biochemistry possible at lightning speed. To grasp why tunneling feels so surreal, picture a hiker trapped in a valley between two mountains. In the classical world, they'd need enough energy to climb over. But in quantum land, there's a chance they'll simply phase through the mountain, emerging unscathed on the other side. This isn't just metaphor, it's math. The Schrödinger equation, quantum mechanics' master formula, predicts this behavior, revealing that particles smear out across space, their wave functions seeping into barriers they can't classically overcome. The thicker or taller the barrier, the lower the odds of tunneling, but for tiny particles like electrons, those odds are very real. Some physicists argue tunneling hints at deeper truths about reality. Could it mean particles briefly borrow energy from the vacuum, defying conservation laws? Or does it suggest barriers aren't as absolute as we think, revealing a universe where impossibilities are merely probabilities in disguise? Whatever the interpretation, one thing's clear: tunneling shatters our intuitive notions of obstacles and boundaries, proving that in the quantum realm, even the most unbreakable walls have invisible doors. And every time your phone turns on or a star flickers in the night sky, you're witnessing this quantum defiance in action. If you've ever tried to focus on a firefly in the dark, you know the harder you stare, the more it seems to dart unpredictably. Just when you think you've pinned it down, it slips away. That's the essence of Heisenberg's uncertainty principle, but instead of fireflies, we're talking about the fundamental building blocks of reality. Werner Heisenberg's revolutionary idea tells us there's a built-in limit to how precisely we can know certain pairs of properties about a particle, like its position and momentum. The more accurately you measure one, the fuzzier the other becomes. It's not a flaw in our tools or a lack of skill. It's woven into the fabric of the universe itself. Think of it like this. Imagine trying to take a photo of a hummingbird in mid-flight. To freeze its motion, you'd need a blindingly fast shutter speed, but that would leave you with a crisp blur, no detail about the bird's position. Slow the shutter down to capture its delicate features, and its wings become a streaky mess. You can't have both at once. In the quantum world, this isn't just a camera limitation, it's a cosmic rule. Measure an electron's position with laser precision, and its momentum becomes a complete mystery. Lock down its speed, and its location dissolves into a cloud of probabilities. This principle doesn't just challenge engineers, it upends philosophy. For centuries, scientists like Laplace dreamed of a perfectly predictable universe where knowing the position and momentum of every particle would let us calculate the future with godlike certainty. Heisenberg's work shattered that illusion. At the quantum level, the universe isn't a clockwork machine, it's a game of dice, where uncertainty isn't a gap in our knowledge but a fundamental feature of existence. But here's where it gets even wilder. The uncertainty principle isn't just about measurement disturbing what we observe. It's deeper than that. Particles don't have definite positions and momenta simultaneously. They exist in a fuzzy state where these properties are intertwined, like two sides of a coin that can't both face up at once. Some interpretations suggest this isn't a limitation but a revelation that the universe is fundamentally probabilistic, a tapestry of potentialities rather than fixed truths. The implications ripple outward. Quantum cryptography exploits uncertainty to create unhackable codes. Any eavesdropper's attempt to measure a particle would disturb it, leaving a telltale sign. Even the vacuum of space isn't immune. So-called quantum foam arises because energy and time are also subject to uncertainty, allowing particles to blink in and out of existence, borrowing energy from nothingness in fleeting violations of classical physics. So what does this mean for us? If the bedrock of reality is uncertainty, does free will exist, or are we just writing quantum probabilities? Is the universe inherently unknowable, or are we missing a deeper layer that would make sense of the chaos? Heisenberg's principle doesn't just draw a line in the sand, it erases the line entirely, leaving us with a universe that's vibrantly, beautifully uncertain. And perhaps that's the most profound lesson of all. The cosmos refuses to be pinned down, inviting us to embrace the mystery rather than conquer it. Empty space is anything but empty. If you could peer into the void between stars with quantum eyes, you'd witness a seething chaos, particles flickering in and out of existence like ghosts at a cosmic masquerade. These are vacuum fluctuations, one of quantum field theory's most startling predictions. According to the rules governing the subatomic world, the vacuum isn't a static nothingness but a bubbling soup of virtual particles that materialize in particle-antiparticle pairs, only to annihilate each other moments later. They exist on borrowed energy, fleeting so fast they evade direct detection, yet their fingerprints are everywhere. Take the Casimir effect, a phenomenon so bizarre it feels like science fiction. Place two uncharged metal plates incredibly close together in a vacuum, and an invisible force pushes them toward each other. Why? Because the space between the plates is so narrow it restricts the types of virtual particles that can form there, while outside the plates, quantum froth continues unabated. The imbalance creates pressure, proof that so-called empty space is alive with transient energy. It's like submerging two bottles in a stormy ocean, then sealing them together. The chaos outside exerts force the calm inside can't match. But here's where it gets cosmic. These fleeting particles might hold the key to one of astronomy's biggest puzzles, dark energy. Observations show the universe isn't just expanding, it's accelerating outward at breakneck speed, as if propelled by some invisible repellent. One leading theory suggests vacuum fluctuations could be the culprit. Every cubic centimeter of space, no matter how empty, contains this quantum energy. Multiply that by the vastness of the cosmos, and you've got a staggering reservoir of power. Some calculations even suggest this vacuum energy could explain the cosmological constant, a term Einstein once called his greatest blunder before astronomers realized the universe really was accelerating. Yet there's a catch. When physicists tally up the predicted energy of these quantum fluctuations, the numbers are off by a factor of 10 to the power of 120. That's not just a rounding error, it's the worst mismatch between theory and observation in all of science. Either we're missing something fundamental about how vacuum energy works, or there's a mysterious cancellation mechanism we've yet to uncover. The implications ripple from the infinitesimal to the infinite. If vacuum fluctuations really drive cosmic acceleration, they're scripting the universe's fate, pulling galaxies apart until space is a cold, lonely void. But they're also shaping technology here on Earth, scanning tunneling microscopes which let us manipulate individual atoms, rely on quantum tunneling through these very fluctuations. Even the atomic stability of matter itself may owe something to the restless energy of the vacuum. So next time you stare at the night sky, remember, the silence between stars is an illusion. Beneath the stillness lies a quantum carnival where particles dance in and out of reality, where nothing is pregnant with potential, and where the fate of the cosmos might hinge on the shortest-lived guests at existence's party. We're just beginning to decipher their chaotic choreography, and it could rewrite everything we know about the universe's beginning, end, and the shimmering void in between. Imagine a tightrope walker performing a flawless act until a gust of wind knocks them off balance, forcing them to step onto solid ground. That's quantum decoherence in a nutshell. The moment a quantum system's delicate superposition collapses into the ordinary, predictable world we recognize. But here's the twist: it's not magic or measurement alone that does this. It's something far more mundane, the environment itself. Every interaction with surrounding particles, a passing photon, a stray air molecule, even the faintest thermal vibration acts like that gust of wind, stripping away quantum weirdness and leaving behind the classical reality we take for granted. Take Schrödinger's cat again. In theory, it's suspended in that eerie alive and dead state, but in reality, the cat isn't isolated. Its fur brushes against the box, its heartbeats jostle atoms, and air molecules bombard it from all sides. Each of these tiny interactions measures the system in a way, forcing the quantum possibilities to resolve into a single outcome long before a human lifts the lid. This is decoherence at work, nature's way of ironing out quantum probabilities until they align with the concrete world we experience. The math behind this is both elegant and profound. Quantum systems are described by wave functions that can span multiple states, like ripples overlapping in a pond. But when the environment interacts with these states, it doesn't just nudge them, it entangles with them. Imagine scribbling a secret message in ink, then dumping a bucket of water over it. The words don't vanish, they smear into illegibility as the water's molecules carry fragments of the ink away. Similarly, as a quantum system entangles with its surroundings, its once coherent states scatter into an irretrievable mess, leaving no trace of superposition behind. This isn't just theoretical. Decoherence explains why quantum computers are so finicky. Qubits must be shielded from even the slightest environmental noise, cooled to near absolute zero, locked away in vacuum chambers because heat or stray EM waves would destroy their fragile superpositions in an instant. It's also why we don't see everyday objects in two places at once. A baseball, for instance, is constantly bombarded by trillions of particles, ensuring any quantum fuzziness vanishes faster than we could ever detect it. But decoherence doesn't just erase quantum effects, it shapes reality's very boundaries. Some physicists speculated could explain the mysterious transition from quantum to classical physics, bridging the gap between the subatomic and the macroscopic. Others wonder if it holds clues to the measurement problem. Perhaps there's no need for conscious observers when the environment is constantly observing everything around us. Yet puzzles remain. Why does decoherence produce the specific classical outcomes we see? Why don't we ever find a cat half alive in a box or a baseball hovering between two bases? Some theories suggest emergent laws or hidden symmetries steer decoherence toward familiar results, but the answer is far from settled. What's clear is this: decoherence isn't a flaw in the quantum world, it's the price of admission to our universe. Without it, reality would be an endless storm of overlapping possibilities, unmoored from logic or locality. Instead, it gives us a world where quantum strangeness hides in the shadows, peeking out only under the most controlled conditions. A reminder that the true magic of existence isn't just in its mysteries, but in the delicate balance that makes them invisible until we know where to look. Einstein never liked the idea of spooky action at a distance. It offended his sense of cosmic order, the belief that reality should be local, that nothing could influence anything else faster than light could travel between them. So in 1935, he teamed up with physicists Boris Podolsky and Nathan Rosen to craft a devastating critique of quantum mechanics, now known as the EPR paradox. Their argument was simple. If quantum theory were correct, measuring one particle could instantly determine the state of another, no matter how far apart they were. To Einstein, this wasn't just weird, it was proof that quantum mechanics must be incomplete, hiding deeper, hidden variables that would restore sanity to physics. The EPR paper laid out a thought experiment with two entangled particles. Measure one's position, and you'd know the others with absolute certainty faster than light could carry that information. Similarly, measuring one's momentum would reveal the others. But here's the catch: quantum mechanics forbids knowing both position and momentum simultaneously, thanks to Heisenberg's uncertainty principle. Einstein saw this as a contradiction. If reality were truly independent of observation, as he believed, then both properties must exist objectively, even if we couldn't measure them. Otherwise, the universe would require particles to communicate faster than light, violating relativity. For decades, this remained a philosophical tug-of-war until physicist John Stuart Bell entered the scene in the 1960s. Bell devised a mathematical way to test whether hidden variables could explain entanglement's weirdness. His theorem set a limit. If experiments showed stronger correlations between particles than any local hidden variables could produce, Einstein's interpretation would collapse. When physicists finally ran the tests, first by Stuart Friedman and John Clauser, then more definitively by Elaine Aspect in the 1980s, the results were unequivocal. Entangled particles displayed correlations that shattered Bell's limit, confirming quantum mechanics predictions. There were no hidden variables. Reality really was that strange. This wasn't just a victory for quantum theory, it deepened the mystery of non-locality. Entanglement doesn't allow faster-than-light communication. You can't use it to send messages, but it does imply a universe where particles share connections transcending space and time. Some interpretations lean into this radical intimacy. Bohmian mechanics, for instance, proposes a pilot wave guiding particles in harmony, while others suggest entanglement reveals a holographic universe where separation is an illusion. Einstein's challenge, meant to expose quantum theory's flaws, ended up revealing its most profound truth. The universe doesn't care about our classical intuitions. It operates by rules that seem impossible until experiments prove otherwise. The EPR paradox didn't break quantum mechanics. It highlighted how much we still have to learn about the fabric of reality. And somewhere in that tension between Einstein's skepticism and quantum weirdness lies a clue to the universe's deepest secrets. What if death isn't the end, but just a door you never walk through? This is the unsettling premise of quantum immortality, a thought experiment that pushes the many worlds interpretation to its logical extreme. Imagine you're strapped into a diabolical machine that has a 50% chance of killing you each time you press a button. From a classical perspective, after a few tries, your odds look grim. But quantum immortality suggests something wild. From your perspective, you might never experience death at all. Every time the machine activates, the universe splits. In one branch, you die. In another, you survive, and it's only in that surviving branch that your consciousness continues. To you, it would feel like beating impossible odds over and over, while in countless parallel realities, your story ends. This isn't just morbid speculation. It's a direct consequence of taking the many worlds interpretation seriously. If every quantum possibility spawns a new universe, then consciousness follows the branches where it persists, like a skimmer hopping across the surface of reality without ever sinking into the depths where existence stops. Some theorists argue this isn't just theoretical. They point to bizarre near-death anecdotes, people surviving against absurd odds, as possible evidence of this branching effect. Of course, there's no way to test it empirically. After all, the version of you that dies can't report back, but the implications spiral far beyond survival. Quantum immortality forces us to confront the nature of consciousness itself. Are we just passive observers riding one thread of reality, or does our awareness actively choose its path? And what happens over cosmic timescales? If consciousness truly follows paths where it endures, could we, without realizing it, be sliding into branches where Earth avoided extinction, where humanity dodged catastrophe? Some even take this further. If advanced civilizations discover how to manipulate quantum branching, could they engineer immortality by steering their descendants into ever-surviving timelines? Ethically, the idea is a minefield. If branching realities are infinite, does anything truly matter? If every choice spawns universes where all outcomes play out, does responsibility dissolve? Philosophers split sharply here. Some argue it renders action meaningless. Others insist that your experience of reality remains singular and urgent. The scientific community largely dismisses quantum immortality as untestable, a philosophical zombie that can't be falsified. Yet it lingers because it exposes the raw nerve between quantum theory and human experience. Physics tells us reality might branch endlessly, but our lives feel linear, finite, real. Perhaps that's the greatest mystery here, not whether we can cheat death, but why we perceive existence as a single, unbroken thread in the first place. In a multiverse of infinite possibilities, how does consciousness stitch together the illusion of continuity? The answer, if there is one, might rewrite not just physics, but the very meaning of being alive. What if everything you see, touch, and experience is nothing more than an illusion, a cosmic sleight of hand? The holographic principle proposes exactly that. Our three-dimensional universe might just be a shimmering projection of information encoded on a distant, two-dimensional surface. Think of it like a credit card hologram, those shiny stickers that seem to contain depth when you tilt them, even though they're flat. But here's the twist, this isn't just a metaphor. Black holes might hold the key to unraveling this mind-bending possibility. It all started with a puzzle about black holes and information. When an object falls into a black hole, classical physics says it's gone forever, swallowed by an inescapable abyss. But quantum mechanics insists information can't be destroyed. So where does it go? In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of hidden information, and that this entropy is proportional not to their volume but to their surface area. Stephen Hawking later showed that black holes slowly evaporate, leaking radiation, which only deepened the paradox. If the information isn't lost, it must be encoded somewhere. But how? Enter the holographic principle. Proposed by Gerard T. Hooft and later refined by Leonard Susskind, it suggests that all the information about objects inside a black hole, or, by extension, the entire universe, might be stored on its boundary like a cosmic hard drive. Just as a hologram encodes a 3D image on a 2D surface, the universe could be projecting its richness from a flat, distant plane we can't perceive. String theory lends weight to this idea, with mathematical models showing how higher dimensional spaces can emerge from lower dimensional ones, like a shadow puppet cast on a wall. But the implications go far beyond black holes. If the holographic principle is true, it means reality as we know it is a kind of illusion, not in the philosophical sense but in a concrete, physical way. The solidity of objects, the vastness of space, even the passage of time could all be emergent properties of a deeper, simpler layer of reality. It's as if we've spent our lives watching a movie, unaware that the true story is written on the celluloid itself. Experiments are already probing this radical idea. Fermilab's holometer, for instance, hunts for quantum fuzziness in space-time, tiny fluctuations that might betray the pixelated nature of reality. And if the principle holds, it could rewrite our understanding of gravity, unifying it with quantum mechanics by revealing space itself as a kind of quantum code. The holographic principle doesn't just challenge our intuition, it turns it inside out. If our 3D world is a projection, what does that say about free will or consciousness? Are we just avatars in a cosmic simulation, or is there something more profound at play? One thing's certain, the universe has a habit of being stranger than we can imagine, and the holographic principle might be the closest we've come to glimpsing the hidden scaffolding behind the show. Time doesn't just pass, it arrows forward, dragging us from past to future with unshakable momentum. Yet if you crack open the equations of quantum mechanics, something bizarre jumps out. They don't care which way time flows. Run them backward or forward, and they work just the same. So why does our universe have such a stubborn preference for one direction? Why do shattered cups never reassemble or candles unburn? This is the enigma of time's arrow, and quantum mechanics might hold the missing piece. Start with entropy, the universe's built-in chaos meter. The second law of thermodynamics says entropy always increases systems' trend toward disorder, not order. That's why your coffee cools down, not heats up, or why shuffling a deck of cards mixes them instead of sorting them. But entropy alone doesn't explain time's arrow at the quantum level. Zoom in far enough and you'll find particles dancing to equations that treat time as perfectly reversible. So where does the irreversibility emerge? Enter the quantum measurement problem. In quantum mechanics, superposition lets particles exist in multiple states at once until they're measured, collapsing into one outcome. This collapse is the only quantum process that seems to pick a direction in time. Before measurement, possibilities fan out like branches, after only one remains. Some physicists argue this collapse injects an arrow into time's symmetry, like a one-way valve for reality. The more collapses happen, the more the universe tips toward higher entropy, locking in time's forward march. But there's a catch. If measurement creates time's arrow, what is measurement? The Copenhagen interpretation says it's observation, but who or what counts as an observer? Experiments with increasingly large quantum systems show decoherence environmental interactions can mimic collapse without conscious observers. Maybe time's arrow emerges from quantum systems constantly measuring each other, a cosmic chain reaction of decoherence that ratchets entropy upward. Another provocative idea ties time's arrow to the Big Bang. The early universe had staggeringly low entropy, a pristine starting point that set the gradient for everything after. Quantum fluctuations in that primordial soup might have nudged the cosmos onto its irreversible path. Some theories even suggest that without quantum indeterminacy, time might not flow at all, a universe of perfect symmetry, frozen in an eternal present. The stakes here are cosmic. If quantum affects seed time's arrow, does that mean other arrows are possible? Could a universe with different quantum rules experience time backward or in loops? And what does it say about free will if time's flow is just statistics playing out on a quantum scale? We're left staring at a paradox. The most fundamental laws of physics don't distinguish past from future, yet our lived reality is drenched in time's unyielding direction. Perhaps the answer lies not in the equations themselves, but in how we, and the universe, choose to read them. Einstein's theory of general relativity paints gravity as the curvature of spacetime, a smooth, continuous fabric bent by mass and energy. But zoom into the quantum realm, and this elegant picture shatters. Here, particles flicker in and out of existence, forces act in discrete packets, and nothing is certain. The problem: gravity refuses to play by quantum rules. For decades, physicists have wrestled with this clash, a divide so deep it hints at missing pieces in our understanding of reality itself. Take black holes. According to relativity, their cores crush into infinite density singularities where spacetime itself breaks down. But quantum mechanics abhors infinities. It demands everything, even gravity, operates in finite, quantized steps. This isn't just academic. Without a quantum theory of gravity, we can't explain what really happens at the Big Bang or inside a black hole's heart. It's like having two rule books for the universe, each flawless in its domain, yet utterly incompatible when forced to meet. Enter loop quantum gravity, one audacious attempt to bridge the gap. Imagine spacetime not as a smooth sheet, but as a fabric woven from tiny, indivisible loops, a mesh so fine it's imperceptible at everyday scales. These loops intertwine, creating the illusion of continuity. Much like a digital photo appears seamless until you pixel stretch it. In this framework, singularities vanish. At the center of a black hole, spacetime doesn't rip, it rebounds like a spring compressed to its limit. The Big Bang, not a singularity, but a big bounce from a prior universe's collapse. It's a radical rewrite of cosmic history, but one that sidesteps relativity's infinities by treating gravity as inherently quantum. Then there's string theory, the most hyped and controversial contender. It proposes that particles aren't dots but vibrating strings, with each note in their symphony corresponding to a different particle or force. Gravity emerges naturally in this framework, but at a cost. The math only works if the universe has 11 dimensions. The extra dimensions, curled up invisibly small, could explain why gravity feels weak compared to other forces. It's leaking into hidden realms. String theory's allure lies in its ambition. It doesn't just quantize gravity, it seeks to unify all forces under one mathematical roof. But critics argue it's untestable, a beautiful theory stranded in a desert of empirical proof. Other approaches prowl the edges of mainstream physics. Causal dynamical triangulation imagines spacetime as a mosaic of tiny, triangular blocks that glue together into classical smoothness at large scales. Entropic gravity suggests gravity isn't a fundamental force at all, but an emergent effect, a cosmic illusion born from the universe's tendency toward disorder. Each theory dances around the same core problem: how to make gravity quantum without breaking reality as we know it. Why does this matter? Because quantum gravity isn't just about equations, it's about the birthplace of time, the fate of black holes, and the origin of everything. Without it, our story of the universe has a hole where the first chapter should be. The quest to reconcile quantum mechanics and relativity isn't just technical, it's existential. It asks what spacetime is at its most fundamental level. and whether the universe in its deepest layers operates by rules we've yet to dream of. One day, a breakthrough might crack this puzzle wide open, revealing a cosmos stranger and more interconnected than we dared imagine. Until then, the struggle to quantize gravity remains science's greatest unfinished symphony, a melody of math and mystery playing just beyond our reach. 95% of the universe is missing. At least that's what the numbers tell us. Ordinary matter, the planets, stars, and galaxies we can see, accounts for a pitiful 5% of the cosmos. The rest, a ghostly duo, dark energy driving the universe's expansion, and dark matter, an invisible scaffold holding galaxies together. But what is dark matter? The leading suspicion: it might be hiding in the quantum shadows, waiting to be unmasked by the very rules that govern the subatomic world. Picture the universe as an iceberg. The visible part, everything we've ever touched or seen, is just the tip. Beneath the surface lurks something far stranger, particles that don't interact with light, that pass through walls like ghosts, yet wield enough gravitational pull to bend the paths of galaxies. These aren't just placeholders for our ignorance. Quantum field theory suggests dark matter could arise from entirely new fields or particles, ones that don't fit the standard model's tidy menu. Take actions, for instance, dreamed up in the 1970s to solve a puzzle in particle physics. These hypothetical particles are feather-light, nearly massless, and barely interact with ordinary matter. But in vast numbers, they could swarm the cosmos, their collective gravity sculpting galaxies. Quantum experiments are hunting them now. Imagine ultra-sensitive detectors cooled to near absolute zero, shielded from cosmic rays, listening for the faintest whisper of an action bumping into an atom. It's like trying to hear a pin drop in a hurricane, yet breakthroughs could be closer than we think. Then there's WIMP, weakly interacting massive particles. Heavier than actions, these hypothetical relics from the Big Bang would zip through space, occasionally nudging atomic nuclei. Underground labs like Italy's Gran Sasso or South Dakota's Eluix Zeppelin use vats of liquid xenon to catch these rare collisions. So far, WIMP remain elusive, but their potential ties to supersymmetry, a theory linking matter and force-carrying particles, keep physicists hooked. But here's where quantum fields enter the fray. If dark matter isn't just particles but a field permeating space, like the Higgs field that gives particles mass, its effects could be even weirder. Some theories propose hidden sectors, parallel quantum realms with their own forces and particles, barely mingling with ours except through gravity. It's as if the universe has secret compartments, and dark matter is the faint echo leaking through the walls. The search isn't just academic. If dark matter particles exist, they might occasionally decay, emitting detectable quantum signals. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies for unexplained gamma-ray bursts that could be their death throes. Other experiments, like CERN Large Hadron Collider, smash protons together at near light speeds, hoping to conjure dark matter from the energy of the crash. Yet the deeper we dig, the stranger the possibilities become. Could dark matter be primordial black holes forged in the universe's first chaotic seconds? Or sterile neutrinos, ghostly cousins to the nearly massless particles that stream from the sun? Each hypothesis stretches our understanding of quantum reality, forcing us to ask, is the cosmos far richer, far stranger than the standard model allows? One thing's certain: dark matter isn't just a placeholder. It's a screaming hint that the quantum world has chapters we've yet to read, particles that defy detection, fields that hum silently in the void, or perhaps something even wilder. And when we finally crack its code, we won't just solve a cosmic accounting error. We'll glimpse the hidden architecture of reality itself. Ever heard the saying, "A watched pot never boils"? In the quantum world, that old adage isn't just folklore, it's a law of physics. Meet the quantum Zeno effect, a phenomenon so counterintuitive it feels like a glitch in reality. The more you stare at an unstable quantum system, the more stubbornly it clings to its current state, refusing to decay or change. It's as if the universe itself hesitates under scrutiny, freezing in place under the weight of observation. The effect gets its name from the ancient Greek philosopher Zeno, who famously argued that motion is an illusion, that an arrow in flight is actually at rest at every instant. While Zeno's paradox was debunked long ago, his ghost lingers in quantum mechanics. Here's how it works. Imagine an unstable particle poised to decay like a ticking time bomb. Left alone, it'll eventually break apart, but if you bombard it with rapid, repeated measurements peeking at it non-stop, something bizarre happens. The act of observation resets the particle's quantum clock, forcing it back to square one. It's like flipping a coin but snatching it mid-air every time it starts to turn. Never give it a chance to land and it'll hover in perpetual limbo. This isn't just theoretical sleight of hand. In the lab, scientists have used lasers to continually watch excited atoms, preventing them from releasing energy as light. The result, atoms stuck in their excited states, defying nature's urge to relax. The quantum Zeno effect reveals a profound truth. Measurement isn't passive. It's an intervention, a way to manipulate reality by sheer persistence. Now imagine harnessing this power in quantum computers. Qubits, those delicate quantum bits, are notorious for losing coherence, crumbling into randomness in a process called decoherence. But what if you could freeze them in their desired states by checking in relentlessly? Some researchers believe the Zeno effect could be the key to error correction, a way to keep qubits stable long enough to perform complex calculations. It's like teaching a tightrope walker to balance by constantly whispering reminders, except here, the reminders are laser pulses or magnetic nudges, but the implications go beyond technology. The Zeno effect blurs the line between observer and participant, suggesting that reality isn't just something we witness, it's something we shape. Ancient yogis claimed focused attention could alter physical states. Quantum mechanics might be proving them right. Whether we're stabilizing qubits or probing the nature of existence itself, one thing's clear: in the quantum realm, watching isn't just seeing. It's holding the universe's hand, guiding it toward the reality we choose to see. For centuries, we've assumed life operates by classical rules, orderly, predictable, bound by the same physics as rolling apples and swinging pendulums. But nature might have been working in quantum shadows all along. Take photosynthesis, the miracle that turns sunlight into life. At its heart lies a paradox. Plants and algae harvest light with near-perfect efficiency, far surpassing anything human engineers can design. The secret: quantum coherence. When photons hit a leaf, their energy doesn't bounce around randomly like a pinball. Instead, it spreads out like a wave, exploring multiple pathways at once to find the quickest route to the reaction center. It's as if the plant performs a quantum computation with every ray of sunlight, exploiting superposition to optimize energy transfer in ways our clumsiest solar panels can only dream of. Then there's the avian compass, the built-in GPS that guides birds across continents. Monarch butterflies and European robins navigate using Earth's magnetic field, but here's the twist: the field is too weak to trigger classical chemical reactions. Enter quantum entanglement. Some scientists believe these creatures harness entangled electron pairs in cryptochrome proteins in their eyes. When these pairs interact with Earth's magnetism, their quantum states shift, painting an invisible map in the bird's mind. It's navigation by spookiness, a biological exploit of one of quantum mechanics' most baffling phenomena, but the most provocative frontier: consciousness itself. The human brain is a storm of electrical impulses, but could quantum vibrations in microtubules, tiny protein structures in neurons, play a role in cognition? Anesthesiology offers a tantalizing clue. Drugs that switch off awareness seem to target these very structures, quieting their quantum oscillations. It's still speculative, but if true, the implications are staggering. The boundary between mind and matter might not be where we thought. Quantum processes could be whispering beneath the surface of thought itself. From leaves that cheat physics to birds that see Earth's hidden grid, nature seems to have mastered quantum mechanics long before we cracked the equations. Maybe life isn't just exploiting quantum weirdness, maybe it's built on it. And if that's the case, the line between biology and quantum physics isn't just blurring. It might not exist at all. Black holes aren't just cosmic vacuum cleaners, they're shredders of reality itself. At least that's what Stephen Hawking shocked the world by claiming in the 1970s. According to his math, black holes don't just swallow matter, they erase the very information that makes that matter unique, like a cosmic incinerator burning the blueprint of existence. This isn't just a poetic metaphor, it's a crisis. Quantum mechanics insists information can never be truly destroyed. Even if you burn a book, the ash and smoke still encode its contents in some scrambled way. But Hawking radiation, the faint glow black holes emit as they evaporate, seem to carry no such fingerprint. If he was right, the universe had a glaring bug. Black holes violated the most sacred rule of quantum physics. The implications sent shockwaves through theoretical physics. If information vanishes in black holes, the past isn't just hard to reconstruct, it's impossible. Cause and effect crumble, predictability dies. This was the black hole information paradox, and solving it would require rewriting our understanding of gravity, quantum theory, or both. Enter the firewall hypothesis, one radical attempt to patch the paradox. Picture an astronaut falling toward a black hole's event horizon. According to Einstein, they'd feel nothing special at first, just a gentle tug as space-time bends. But quantum mechanics suggests something far more violent, a searing wall of energy, a firewall that vaporizes the traveler before they cross the horizon. This firewall would preserve information by encoding it in the explosion, but at a brutal cost. Relativity's smooth space-time would shatter at the horizon, replaced by a quantum inferno. Yet there's another, even stranger solution. Remember the holographic principle. It suggests all the information swallowed by a black hole isn't lost. It's smeared across its event horizon like a cosmic etch-a-sketch. As particles fall in, their data gets imprinted on the horizon's surface in scrambled form, only to re-emerge in Hawking radiation as the black hole decays. This holographic resolution elegantly saves quantum mechanics, but it turns reality into a cosmic sleight of hand. The three-dimensional world we experience might just be a projection of two-dimensional information, like a movie playing on the universe's ultimate projector screen. The stakes here are cosmic. If information can escape black holes, it implies a universe where nothing is ever truly gone, just transformed, encrypted, or hidden. Quantum gravity theories like string theory and loop quantum gravity hinge on this puzzle. Even practical technologies like quantum computing could feel the ripple effects since their power relies on information preservation. But the deepest lesson might be philosophical. Black holes aren't just destroying matter, they're testing the limits of human knowledge itself. Every solution we propose forces us to confront how little we grasp about the nature of reality and how much stranger the truth might be. After all, if the universe's most destructive objects are also its most meticulous librarians, what other contradictions are waiting to be uncovered? We often think of particles as the universe's building blocks, tiny marbles of matter bouncing through space, but dig deeper and this picture crumbles. The real foundation of reality isn't solid at all. It's a shimmering, seething ocean of quantum fields. Imagine space as an infinite grid of interconnected springs, each vibrating at different frequencies. What we call particles, electrons, quarks, photons, are just momentary ripples in these fields, like notes plucked on a cosmic harp. An electron isn't a thing, it's an excitation of the electron field, a tiny knot of energy in an invisible fabric that stretches across the universe. This shift from particles to fields isn't just philosophical, it's revolutionary. In classical physics, particles are discrete objects with fixed properties. But quantum field theory reveals a universe where emptiness is an illusion. The vacuum isn't empty, it's a hive of potential with fields humming at their lowest energy, ready to erupt into particles with the right nudge. Even in the darkest void, quantum fields never sleep. Virtual particles flicker in and out of existence, borrowing energy from nowhere, their fleeting lives governed by uncertainty. This isn't poetic license, it's math. The Higgs field, for instance, isn't just some abstract idea. It's what gives particles mass by dragging on them as they move, like wading through molasses. Without it, electrons would zip around at light speed, atoms would never form, and life as we know it would be impossible. Yet for all its power, the quantum field framework raises dizzying questions. If fields are everywhere, why do we only perceive particles? The answer lies in quantization. The way fields bundle energy into discrete packets we interpret as particles. Think of a guitar string. It can vibrate at specific frequencies, producing distinct notes. Similarly, quantum fields ring at particular energies, and we experience those resonant peaks as particles. But here's the catch: fields themselves are continuous. The particle-like behavior emerges from how we interact with them, like mistaking ocean waves for individual droplets because we can only scoop up water by the cupful. This duality, fields versus particles, also redefines forces. Take electromagnetism. Classically, we imagine electrons repelling each other by exchanging photons like tennis balls. But in quantum field theory, photons are excitations of the electromagnetic field, and the exchange is just the field's oscillation propagating between charges. Even gravity, stubbornly resistant to quantization, might ultimately be a field, one we've yet to fully understand. The lingering mystery, why these specific fields, vibrating in these precise ways, give rise to our universe. Could there be other fields, undiscovered or hidden, governing invisible realms? Some theories, like supersymmetry, propose entire families of shadow fields waiting to be detected. Others suggest fields might not be fundamental at all, but emergent, like temperature arising from atomic motion. Quantum fields don't just underpin reality, they dissolve the line between matter and emptiness, between what's there and what's possible. They whisper a radical truth: the universe isn't made of things, it's made of symphonies, and every particle, every force, every flicker of existence is just one note in an endless, unfolding composition. What if every choice you've ever made, and every one you didn't, is playing out somewhere else in a reality just as real as this one? This isn't science fiction. It's the startling claim of the many worlds interpretation, a radical solution to quantum mechanics' strangest puzzles. Picture Schrödinger's cat again, not just alive or dead in a box, but with the universe splitting at the moment of observation, spawning one branch where the cat lives and another where it dies. There's no collapse of the wave function, no single outcome. Instead, reality endlessly branches, creating a multiverse where every quantum possibility becomes concrete. The math behind this is deceptively simple. Quantum states evolve deterministically, like clockwork, but when a system interacts with its environment, it doesn't collapse, it entangles. From the perspective of someone inside a branching event, only one outcome seems real, but the universe itself doesn't pick sides. It embraces every possibility, spinning off worlds where you took that job abroad, where dinosaurs never went extinct, where the laws of physics themselves are subtly different. It's a cosmic kaleidoscope, fracturing with every quantum decision. Yet the many worlds interpretation isn't the only multiverse game in town. Cosmic inflation, the theory that the early universe underwent exponential expansion, suggests our observable cosmos might be one bubble in an endless froth of universes, each with its own unique physics. Unlike quantum branching, these bubbles aren't tied to observation, they're accidents of spacetime's explosive birth. Then there's string theory's landscape, which posits 10 to the power of 500 possible vacuum states, each corresponding to a different universe with its own constants and forces. In this view, we're not just one universe among many, we're one possibility among countless others, a fluke in an infinite ensemble. So how do we test these ideas? For many worlds, the challenge is stark. By definition, branching universes are inaccessible. But some theorists hunt for quantum echoes, subtle signs that nearby worlds briefly interfere with ours. Others argue that if many worlds is true, conscious observers should statistically find themselves in the most probable outcomes, a controversial idea called quantum immortality. Inflationary multiverses leave potential fingerprints in the cosmic microwave background, anomalies that might hint at collisions with other bubbles. And string theory's landscape could be probed by measuring whether our universe's constants are finely tuned, suggesting selection from a vast ensemble. Critics dismiss multiverses as untestable metaphysics, a retreat from science's empirical roots. Why believe in infinite unseen worlds when Occam's razor favors simplicity? Defenders counter that these theories emerge naturally from well-established physics, quantum mechanics, inflation, string theory, and that rejecting them might mean ignoring the universe's true complexity. At its core, the multiverse debate isn't just about parallel realities, it's about the nature of existence itself. Is the cosmos a single, elegant equation or a teeming library of possibilities? Are we lonely witnesses to one thread of history, or just one audience member in a theater of infinite acts? The answer, if there is one, might rewrite not just physics but our place in the grandest story of all. Butterflies flapping their wings might cause hurricanes, but in the quantum world, a single particle's uncertainty can unravel the entire cosmos. This is quantum chaos, the mind-bending phenomenon where microscopic randomness snowballs into large-scale unpredictability, blurring the line between the quantum realm and the chaos we see in everyday life. At its core, it's a cosmic game of dominoes where the tiniest nudge at the atomic scale can cascade into planetary-scale disorder over time. Take something as simple as a molecule's vibration. In classical physics, if you could measure every atom's position and momentum perfectly, you could predict its future path with absolute certainty, but quantum mechanics shatters that illusion. Heisenberg's uncertainty principle means we can never pin down a particle's state completely, and those minuscule uncertainties don't just stay small. Like a misspelled word in a recipe, they propagate, twisting and amplifying until the system's behavior becomes utterly unpredictable. This isn't just theory. Quantum chaos lurks in everything from the erratic orbits of electrons in heavy atoms to the frenzied dance of particles in superheated plasmas, where initial conditions are forever lost in a storm of probabilistic fog. The strangest part, quantum chaos isn't pure randomness, it's randomness with a hidden order. Imagine rolling a die, but instead of landing on numbers, it lands on intricate patterns that, while unpredictable, still follow deeper mathematical symmetries. This delicate balance between disorder and structure is what makes quantum chaotic systems so devilishly hard to model. Even with supercomputers, tracking a quantum system's evolution over long timescales is like trying to forecast the weather on a planet where the laws of physics rewrite themselves every nanosecond. Now, here's where it gets cosmic. Quantum chaos might be the missing link between the microscopic and the macroscopic, explaining why the universe evolves from quantum certainty at the Big Bang to the tangled complexity we see today. Some theorists suggest that black holes, those ultimate chaos engines, are quantum chaotic systems par excellence, their interiors churning with unpredictability that leaks out as Hawking radiation. Others see quantum chaos as the reason time itself has an arrow, with microscopic fluctuations amplifying into the irreversible entropy that defines our everyday experience. Yet for all its destructive potential, quantum chaos isn't all doom and unpredictability. It's also a creative force. The same sensitivity that makes quantum systems uncontrollable also powers phenomena like high-temperature superconductivity, where electrons coordinate in chaotic harmony to defy classical resistance. Quantum computers, too, might one day harness controlled chaos to solve problems that stump ordinary machines, turning the butterfly effect into a computational superpower. So what's the takeaway? Quantum chaos teaches us that the universe isn't just uncertain, it's unstably uncertain. The same quantum rules that let particles exist in multiple states also ensure that those states spiral into complexity too vast to ever fully predict. Whether shaping the fate of stars or the limits of human technology, chaos isn't the exception in the quantum world, it's the rule. And in that chaos lies both our greatest challenges and our most extraordinary opportunities. At the heart of quantum mechanics lies a great vanishing act, one that happens all around us every second without us even noticing. The subatomic world buzzes with superposition, entanglement, and uncertainty, yet the world we see, the world of cars and coffee cups and crashing waves, obeys the predictable, concrete rules of classical physics. So where does the quantum weirdness go? Why don't we see cats both alive and dead, or tennis balls suddenly teleporting across courts? This is the mystery of the quantum classical boundary, and cracking it might reveal how reality itself takes shape. Start with a simple observation. Quantum effects thrive in isolation. A single electron can exist in multiple places at once, but a baseball can't. The difference. Scale matters, but not in the way you might think. It's not just size that suppresses quantum behavior, it's interaction. Every time a quantum system bumps up against its environment, whether it's a photon of light, a stray air molecule, or even the thermal jitter of its own atoms, its delicate superposition gets scrambled. This is decoherence in action, the process by which quantum probabilities collapse into classical certainties. Picture a spinning top. Left alone, it spins smoothly, but the moment it brushes against the table, friction slows it down. Similarly, particles slow down their quantum behavior when constantly jostled by their surroundings. But decoherence isn't the only player. Some theories propose more radical mechanisms. Take objective collapse models, which suggest wave functions. The mathematical descriptions of quantum states collapse spontaneously, not because of observation, but due to hidden instabilities in the fabric of reality itself. Imagine a universe with built-in reset buttons that kick in when quantum systems grow too large or complex, forcing them to choose a state. Experiments like the Gran Sasso Underground Lab in Italy are hunting for signs of this spontaneous collapse, using ultra-sensitive detectors to see if large molecules behave differently when shielded from environmental noise. Energy, too, plays a pivotal role. Quantum effects like tunneling or interference thrive in low-energy environments. Cool a system to near absolute zero, and electrons start surfing through barriers like ghosts. Heat it up and thermal energy drowns out quantum delicacy. This is why superconductors, materials that carry electricity without resistance, only work in frigid conditions. The hotter things get, the more classical physics takes over, like static drowning out a radio signal. Yet complexity itself might be the ultimate quantum killer. A single atom can hover in superposition, but a trillion atoms, like those in a speck of dust, collectively vote through their interactions, averaging out into classical certainty. It's the difference between a single voter swaying an election and a landslide consensus. Some researchers even argue that gravity, often negligible at quantum scales, becomes a silent enforcer of classicality for massive objects. The faintest gravitational tug could be enough to pin down reality's fuzzy edges. The implications go beyond theory. Quantum computers face constant battle with decoherence, their qubits crumbling into classical bits if not meticulously shielded. Understanding the quantum classical boundary could help us build better quantum tech, or even uncover new physics bridging the gap between general relativity and quantum mechanics. But deeper still, this mystery forces us to ask, is the classical world an illusion, a statistical mirage emerging from countless quantum interactions? Or is there a fundamental threshold where reality clicks into a new set of rules? The answers might rewrite not just physics, but our sense of what's real. Because if quantum behavior never truly vanishes, if it's just hidden beneath layers of noise and scale, then the solid world we take for granted is far more fragile, far more magical than it seems. And that's a boundary worth crossing. Imagine a world where information could be stored not in fragile bits or even quantum superpositions, but in the very shape of reality itself, where the difference between a donut and a coffee cup could be the key to unbreakable quantum computing. This isn't abstract math. It's the frontier of topological quantum states, a realm where particles defy classical labels and instead encode data in knots and twists of spacetime so robust, even the universe struggles to untangle them. At the heart of this mystery are enigmas, particles that exist only in two dimensions and remember their past like cosmic scribbles in a notebook. Unlike electrons or photons, which return to the same state when swapped, enigmas carry a memory of their journey. Move one around another, and their quantum states braid like strands of a rope, retaining information about their path. This isn't just theoretical. In ultra-thin layers of certain materials, like semiconductor sandwiches chilled to near absolute zero, electrons collectively behave as enigmas, their interactions governed by topology, the mathematical study of shapes that stay the same when stretched or twisted. Why does this matter? Because topology is the ultimate armor against quantum chaos. In ordinary quantum systems, a single stray photon or vibration can scramble information, a nightmare for quantum computers. But topological states don't store data in easily disturbed properties like spin or charge. Instead, they encode it in global patterns, the way a donut's hole can't be erased by squishing the dough. You can deform the system all you want, the information remains locked in the structure, resistant to local noise. It's like writing a message in the knots of a net rather than the threads. No matter how you shake it, the knots hold firm. This robustness isn't just theoretical promise. Microsoft's Station Q Lab and others are betting big on topological quantum computing, where qubits are replaced by enigmas braided in precise patterns. Get the braids right, and errors that would crash ordinary quantum calculations simply can't happen. It's a paradigm shift from fighting decoherence to designing systems where decoherence barely matters. But the implications go beyond technology. Enigmas hint at a deeper truth. The universe might harbor phases of matter we've barely begun to imagine. Just as superconductors and superfluids revealed new quantum landscapes in the 20th century, topological materials could rewrite the rules of collective behavior in the 21st. Some theorists even speculate that spacetime itself might emerge from entangled topological states, like a 3D projection of a deeper, knotted reality. For now, the search continues. Labs race to stabilize enigmas at higher temperatures, while mathematicians map ever weirder topological phases. One thing's clear, in a quantum world desperate for stability, topology offers a lifeline, not by resisting chaos, but by bending it into something unbreakable. The donut might just save the future of computing, and in the process reveal how deeply geometry is woven into the fabric of existence. Of all the numbers that shape our universe, few are as perplexing as the fine structure constant. Roughly equal to 1/137, this seemingly random value dictates how tightly electrons cling to atoms, how light interacts with matter, and ultimately why chemistry and life itself works the way it does. Unlike most constants, it's dimensionless, a pure number without units, making it a tantalizing clue that nature's deepest laws might be simpler than we think. The story starts with Arnold Sommerfeld, the physicist who first introduced this constant in the early 20th century while refining Bohr's model of the atom. But it was Paul Dirac who became obsessed with it. To him, 1/137 wasn't just a parameter, it was a riddle waiting to be solved. He once mused that a theory explaining this number would unlock the secrets of quantum electrodynamics, the dance of electrons and photons that underpins reality. Yet decades later, we still don't know why it holds this exact value. Some theorists argue it's arbitrary, a roll of the cosmic dice. Others suspect it's a signpost to deeper physics, a thread connecting the known forces to something grander. What makes this constant so strange is its universality. Whether you measure it in a lab on Earth or in the light of distant quasars billions of years ago, its value remains the same. It's as if the universe stamped this number into the fabric of electromagnetism and then never budged. Tweak it even slightly, and the consequences are catastrophic. A few percent higher, and stars would burn through their nuclear fuel too quickly for life to arise. A few percent lower, and atoms wouldn't bond, leaving the cosmos a sterile sea of scattered particles. This razor-thin balance has fueled wild speculation. Could the fine structure constantly be derived from some elegant equation we've yet to discover? String theorists have tried tying it to the geometry of hidden dimensions. Others propose it emerges from the chaotic froth of the early universe, frozen into place during cosmic inflation. There's even a fringe idea that it might not be constant at all, that it varies imperceptibly across space or time, a hypothesis astronomers are testing by analyzing the spectra of ancient starlight. But perhaps the most startling possibility is that 1/137 is a mathematical signature of a deeper symmetry, a hidden pattern waiting to be uncovered. Like pi or the golden ratio, it might be a fundamental truth woven into the structure of reality itself. Until we crack its code, this humble number remains one of physics' greatest open questions, a whisper from the universe that there's still so much left to understand. Time crystals sound like something straight out of science fiction, matter that moves in a repeating pattern, not because it's pushed or powered, but because it's fundamentally unable to sit still. Imagine a clock that ticks forever without winding, or a pendulum that swings eternally without any initial push. That's the essence of a quantum time crystal, a structure that breaks time symmetry, oscillating indefinitely in its lowest energy state, defying one of the most fundamental expectations of physics, that systems should settle into equilibrium. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, who wondered if matter could exhibit motion even at absolute zero, the state of minimum energy where all classical movement ceases. Critics dismissed it as impossible, arguing it would violate the laws of thermodynamics. Yet just 5 years later, two teams, one at Harvard, another at the University of Maryland, brought time crystals to life in the lab. They didn't achieve perpetual motion machines, but something far stranger. Quantum systems locked into rhythmic patterns that repeat not in space but in time. Here's how they pulled it off. The Maryland group used a chain of ytterbium ions-charged atoms suspended in electromagnetic fields. By flipping the spins of these ions with precisely timed laser pulses, they forced the system into a state where it couldn't settle into equilibrium. Instead, the ions began oscillating at twice the period of the laser's rhythm, like a bell ringing at half the speed it struck. This wasn't driven motion, it was a spontaneous breaking of time symmetry, the temporal equivalent of how ice crystals break spatial symmetry by forming orderly lattices from chaotic liquid. Meanwhile, the Harvard team took a different approach, using nitrogen vacancy centers in diamonds, tiny defects where nitrogen atoms replace carbon. When they prodded these defects with microwaves, the spins of nearby electrons synchronized into a stable, self-repeating cycle. Remarkably, these cycles persisted even as the system lost energy, proving this wasn't about energy conservation, but about quantum order emerging from disorder. What makes time crystals so revolutionary is their defiance of equilibrium. Normally, systems trend toward chaos, like steam dispersing in air or coffee cooling to room temperature. Time crystals sidestep this fate by finding a loophole in quantum mechanics. Their oscillations don't require energy input because they're already in the ground state. They're not perpetual motion, they're perpetual structure, like a dance frozen into the fabric of reality itself. But the implications go beyond theoretical curiosity. Time crystals could reshape quantum computing by creating ultra-stable qubits resistant to decoherence. Their predictable rhythms might serve as perfect timekeepers for next-generation atomic clocks. Some theorists even speculate they could model exotic phases of matter in extreme environments, like neutron stars or the early universe, where conventional thermodynamics breaks down. Yet mysteries remain. Are time crystals truly stable over infinite time, or do they eventually decay? Can they exist at higher temperatures, or are they forever confined to frigid, controlled labs? And most tantalizingly, could they teach us about time itself? If matter can encode rhythm in its quantum structure, does that mean time is more than a backdrop? Could it be an active participant in the universe's deepest laws? For now, time crystals stand as one of quantum physics' most poetic discoveries, matter that refuses to stay still, dancing to a rhythm written into the universe's smallest scales. They're a reminder that even in the coldest, quietest corners of existence, there's no such thing as true stillness, only motion waiting to be uncovered. Imagine flipping a coin and watching it spin in the air only to realize, after it lands, that your decision to look at it somehow changed whether it came up heads or tails halfway through its flight. That's the essence of the quantum eraser experiment, a mind-bending demonstration that reality doesn't just defy our expectations, it rewrites the rules of cause and effect entirely. At the heart of this mystery is a twist on the classic double-slit experiment. Fire particles like photons or electrons at a barrier with two slits, and they'll create an interference pattern on the screen behind it, acting like waves that pass through both slits simultaneously. But if you try to spy on which slit each particle actually goes through, the interference vanishes. The particles suddenly act like well-behaved little bullets, as if they're ashamed of their quantum weirdness under scrutiny. Now here's where it gets unreal. In the delayed choice quantum eraser, physicists take this a step further by adding a devious trick. They mark which path each particle takes with a tag like a secret quantum fingerprint, but then give themselves the option to erase that information after the particle has already hit the detector. The result, if the path information is erased, the interference pattern magically reappears even though the particles are already done with their journey. It's as if the particles retroactively decide whether they were waves or particles based on something that happens after they've supposedly made their choice. Picture this as a cosmic game of hide and seek where the rules are written in disappearing ink. You send a photon flying toward the slits, and it leaves a trail of breadcrumbs polarization markers that could tell you which path it took. But instead of reading them right away, you stash the breadcrumbs in a vault. Only later, once the photon has already hit the screen, do you decide whether to unlock the vault and peek at the path data, or burn the clues entirely. Burn them and it's like the photon always traveled both paths as a wave. Keep them and it collapses into a single particle-like history, the kicker. This decision, to preserve or erase, seems to reach backward in time, altering what the photon did before you even made up your mind. What does this mean for our understanding of reality? One interpretation is that quantum events don't become fixed until the full context of observation is settled. There's no objective past until the universe has all the receipts. Another, even wilder take is that time itself might be an illusion, that cause and effect are flexible, and the future can smooth out the wrinkles of the past. Some theorists suggest this hints at a block universe where all moments in time exist simultaneously, and our perception of a linear flow is just a trick of consciousness. Practical implications: quantum erasure isn't just a parlor trick. It's the backbone of protocols like quantum cryptography, where information can be secured by the very act of erasure, like a self-destructing message that was never read. And on a philosophical level, it forces us to ask, if observation can rewrite history, what else might be up for grabs? Are there cosmic undos happening all around us, invisible edits to the script of reality? The quantum eraser doesn't just blur the line between past and present, it smudges it with existential fire. It's a reminder that in the quantum realm, the universe doesn't just keep secrets. It burns the evidence, and sometimes it lets us play with the ashes. The universe should be teeming with life, with billions of galaxies, each hosting billions of stars and planets. The numbers scream that aliens ought to be everywhere. And yet silence. This is the Fermi paradox, the glaring contradiction between the high probability of extraterrestrial civilizations and the total lack of evidence for them. But what if we've been looking in the wrong dimensions? Quantum mechanics might hold the key to this cosmic silence, not in the stars, but in the very fabric of reality itself. Consider the many worlds interpretation of quantum mechanics, where every decision spawns alternate timelines. In this vast multiverse, civilizations might rise and fall across countless branches, but with one eerie catch. The timelines where societies survive long enough to colonize the galaxy could be vanishingly rare. Most civilizations might hit quantum dead ends, timelines where nuclear war, climate collapse, or rogue AI wipe them out before they achieve interstellar travel. We wouldn't hear from those branches because they're cut short, and the few that survive, they might be so scattered across parallel realities that the odds of overlapping with our timeline are astronomically low. It's less a great filter than a quantum sieve, where only the rarest threads of existence weave civilizations durable enough to persist. Then there's the observer effect on a cosmic scale. If advanced civilizations harness quantum technologies, say, by using entanglement for communication, they might inadvertently collapse their own observable universe. Imagine a species engineering space-time itself, tweaking the constants of nature to suit their needs. In doing so, they could destabilize the very quantum fields that make their reality habitable, vanishing into a superposition of failed experiments. Their silence wouldn't be a choice but a consequence of probing too deeply into the quantum code of the universe. Or perhaps alien civilizations are everywhere, just not in forms we recognize. Quantum biology suggests life might exploit phenomena like entanglement or tunneling. What if advanced beings exist as coherent quantum states spread across stars or even black holes? To them, our radio signals and probes might be as meaningless as a single electron spin in a galaxy-sized quantum computer. Their messages could be written in the subtle decoherence of neutron stars or the interference patterns of dark matter, channels we haven't even thought to tune into. The darkest possibility, quantum suicide on a species level. If civilizations inevitably develop technologies that let them manipulate their own timelines, erasing catastrophic events or branching into safer realities, the versions we detect are the ones that didn't survive the experiment. Every observable universe becomes a cemetery of collapsed possibilities, with our timeline just one of countless graves. The Fermi paradox has never been just about space. It's about the nature of existence, and if quantum mechanics teaches us anything, it's that existence is far stranger, far more fragile than we ever imagined. The silence isn't empty, it's alive with shadows, echoes of civilizations that might have been, or might yet be, in realities we'll never see. The answer to where is everybody might not lie in the stars, but in the quantum static between them. Could consciousness itself be a quantum phenomenon? The idea sounds like it's ripped from the pages of a sci-fi novel, but some scientists argue it might be the key to understanding the most elusive aspect of existence, the nature of our own minds. At the heart of this radical theory are microtubules, tiny protein structures inside neurons that form a scaffold-like network in brain cells. According to physicist Roger Penrose and anesthesiologist Stuart Hameroff, these microtubules aren't just cellular infrastructure. They could be quantum computers orchestrating the symphony of consciousness through vibrations dancing at the subatomic level. Penrose and Hameroff's theory, dubbed orchestrated objective reduction (ORCH), suggests that consciousness arises when quantum superpositions within microtubules collapse, creating fleeting moments of awareness. Picture it like this: inside every neuron, microtubules hum with quantum vibrations, existing in multiple states simultaneously. When these vibrations reach a critical threshold, they collapse into a definitive state, and that collapse, guided by the universe's fundamental geometry, as Penrose speculates, generates a moment of conscious experience. It's as if each thought, each flicker of self-awareness is a quantum note in a grand cosmic melody. But why microtubules? Hameroff points to their intricate structure: hollow tubes made of tubulin proteins that can switch between two states, much like the bits in a computer, but with a quantum twist. These tubulins, he argues, could exploit quantum effects to process information in ways classical neurons can't. Even more provocatively, the theory proposes that anesthesia works by silencing these quantum vibrations, effectively turning off consciousness by stabilizing microtubules in a single state. The scientific community's response, a mix of fascination and fierce skepticism. Critics highlight the biggest hurdle: the warm, wet, chaotic environment of the brain. Quantum states are notoriously delicate, typically requiring near absolute zero temperatures and perfect isolation to avoid decoherence. The brain, by contrast, is a noisy, jostling place where molecules collide constantly. How could fragile quantum superpositions survive there? Yet there are intriguing hints that nature might have found a way. Photosynthesis, as we've seen, relies on quantum coherence to shuttle energy through plants with near-perfect efficiency. Some birds navigate using quantum entanglement. If biology can exploit quantum effects in these systems, why not in the brain? Recent experiments have even reported evidence of quantum vibrations in microtubules, though these findings remain hotly debated. For Penrose, the motivation runs deeper than biology. He ties consciousness to the very fabric of reality, suggesting that quantum collapses in microtubules are linked to gravitational perturbations in spacetime, a wild fusion of quantum mechanics and general relativity. In this view, consciousness isn't just a byproduct of neural firings. It's a fundamental feature of the universe, as intrinsic as gravity or light. The implications are staggering. If ORCH is correct, it could bridge the infamous hard problem of consciousness, explaining how subjective experience emerges from inert matter. It might also redefine death, suggesting that quantum information in microtubules could persist in some form, a notion that edges into the territory of near-death experiences and even speculative ideas about a quantum soul. Yet for all its elegance, the theory remains on the fringe. Mainstream neuroscience leans hard into classical explanations, modeling the brain as a vastly complex but ultimately classical computer. And without direct, irrefutable evidence of quantum processes driving cognition, ORCH risks remaining a beautiful hypothesis, one that challenges our assumptions but hasn't yet rewritten the textbooks. Whether Penrose and Hameroff's vision holds up or crumbles under scrutiny, their boldness forces us to ask profound questions. Is consciousness a fluke of biology, or does it tap into deeper layers of reality? Are we classical machines or quantum orchestras? The answer, if there is one, might not just change neuroscience, it could redefine what it means to be alive in a quantum universe. What if everything you've ever known, every star, every atom, every fleeting thought, is just lines of code in an unfathomably advanced simulation? The simulation hypothesis, once relegated to sci-fi and late-night dorm room debates, has clawed its way into serious scientific discourse, and quantum mechanics might be holding the door wide open. Think about it. Our universe runs on discrete, quantized rules. Energy isn't smooth but comes in chunks like pixels on a screen. Particles pop in and out of existence, their properties undefined until measured, as if rendering only when observed. Even the speed of light feels suspiciously like a processing limit, a cosmic frame rate preventing the system from crashing. Coincidence or clues baked into the fabric of reality. Start with the observer effect, quantum mechanics' most infamous quirk. Particles don't have definite states until we look at them, collapsing their wave functions into concrete outcomes. In a simulated universe, this makes terrifying sense. Why waste computing power rendering every particle in full detail until a conscious observer demands it? It's the ultimate optimization hack, like a video game that only loads the graphics when a player turns to face them. Even more telling, quantum entanglement, where particles instantaneously coordinate across vast distances. In a simulation, this spooky action could simply be two variables sharing a hidden pointer in the code, updating simultaneously because they're fundamentally linked at the programming level. Then there's the unsettling precision of nature's constants. The fine structure constant, the gravitational constant. These numbers are dialed in with razor-sharp accuracy, enabling stars, atoms, and life itself. Tweak them slightly and the universe falls apart. To simulation theorists, this isn't luck, it's fine-tuning. Like a programmer adjusting parameters until the virtual world stabilizes, some intelligence might have set these values deliberately. Even mathematical abstractions, like the fact that our universe runs on elegant, computable equations, hint at an underlying architecture designed for processing efficiency. But here's where the debate explodes. Is this science or philosophy? Physicist Silas Bean and colleagues once argued that if we're in a simulation, there might be glitches, artifacts of a lattice-based reality. Just as pixels impose a minimum resolution, spacetime itself could have a fundamental graininess at the Planck scale. Others, like Neil deGrasse Tyson, counter that the hypothesis is inherently unfalsifiable, a clever metaphor with no testable predictions. Meanwhile, philosophers like Nick Bostrom frame it as a statistical inevitability. If civilizations eventually run ancestor simulations, the odds favor us being inside one. Yet the most tantalizing question isn't whether we're in a simulation, but what it would mean if we were. Would the programmers be gods or just grad students in a higher dimensional lab? Could we someday hack the system, exploiting quantum quirks to rewrite our own code? And if reality is virtual, does that make consciousness the ultimate substrate, the one thing that can't be simulated, only experienced? The simulation hypothesis doesn't just blur science and philosophy, it smashes them together, forcing us to confront whether the universe is a cosmos or a construct. And in that collision, we might find something even stranger, that the answer doesn't matter. Because whether this is base reality or an elaborate illusion, the rules are consistent enough to explore, to wonder, and to keep asking the question in the first place. Why does the universe play by quantum rules at all? It's a question so fundamental we rarely stop to ask it. After all, quantum mechanics works. Its predictions are astoundingly precise, its technologies shape our world, and its equations describe reality with eerie accuracy. But step back for a moment and the strangeness hits you. Why should particles exist in ghostly superpositions? Why should observation force reality to pick a state? Why does entanglement stitch the cosmos together with invisible threads? For all its power, quantum mechanics feels less like a complete theory and more like a set of rules we've reverse-engineered from the universe's behavior without ever understanding why those rules exist in the first place. To appreciate the mystery, imagine a universe running on classical physics instead. Here, particles would have definite positions and momenta at all times. Light would be purely a wave or purely a particle, not both. Cause and effect would unfold predictably, with no room for uncertainty or probabilistic jumps. It's a clean, intuitive cosmos, one that aligns with our everyday experience. And yet, it's a universe where atoms couldn't exist as we know them. electrons, no longer smeared into probabilistic clouds, would spiral into the nucleus, annihilating matter in seconds. Chemistry would collapse, stars wouldn't shine, life, if it could emerge at all, would be unrecognizable. Quantum mechanics isn't just a quirk, it's the scaffolding holding reality together. So where did these rules come from? One tantalizing possibility is that quantum mechanics isn't the deepest layer of reality. It's the emergent surface of something even more profound. Think of it like thermodynamics. We once thought heat and pressure were fundamental, until we discovered they arose from the chaotic dance of atoms. Could quantum weirdness similarly bubble up from hidden dynamics we've yet to uncover? Some theories suggest yes. Pilot wave theory, for instance, posits that particles are guided by unseen, hidden variables, their paths deterministic but too complex to track. Others, like quantum Bayesianism, argue that probabilities aren't inherent to nature but reflect our incomplete knowledge, a cosmic game of incomplete information. Then there's the radical idea that quantum mechanics itself might be a shadow of something entirely unexpected. Could spacetime's structure arise from entangled quantum bits as suggested by holographic principles? Might gravity, still resisting quantization, hold the key to unifying these rules? Or could the universe be computational at its core, with quantum mechanics as its operating system, a set of algorithms governing how information flows? The unsettling truth is we don't know. Quantum mechanics might be the final word, a fundamental framework with no deeper explanation. Or it might be a placeholder, waiting for a theory so transformative it makes quantum weirdness look obvious in hindsight. Either way, the search forces us to confront the limits of human intuition. We're creatures evolved to navigate a middle-sized world of apples and orbits, trying to decode a reality that operates on alien logic. And that's the beauty of the puzzle. Every quantum mystery we've explored, from superposition to entanglement, from the measurement problem to the nature of time, isn't just a challenge to solve. It's a signpost pointing toward something deeper, a whisper that the universe has layers we've only begun to scratch. Whether we're on the brink of a revelation or forever chasing shadows, one thing's certain: the quantum world refuses to be ordinary. And perhaps that's the greatest clue of all, that reality at its heart is stranger than we can imagine, not just stranger than we do. From Schrödinger's cat hovering between life and death to particles that vanish and reappear across spacetime, these 30 quantum mysteries aren't just curiosities, they're cracks in the foundation of reality itself. Each one chips away at our classical intuitions, revealing a universe far wilder than Newton or Einstein ever imagined. Think about entanglement, where particles communicate instantaneously across galaxies, laughing at the speed of light. Or superposition, where objects exist in multiple states until observation forces them to choose. Even the vacuum of space isn't empty, it's a seething quantum foam where particles blink in and out of existence, borrowing energy from nothingness. And let's not forget the measurement problem, which asks whether reality even exists without an observer to pin it down. These puzzles aren't isolated quirks, they're interlocking pieces of a grand cosmic puzzle. The double-slit experiment isn't just about waves and particles. It hints that the universe refuses to make up its mind until we force the issue. Time crystals and topological quantum states suggest matter can defy equilibrium, dancing to rhythms written into the fabric of reality itself. And the holographic principle blurs the line between dimensions, proposing that everything we see might be a 2D projection on the edge of the cosmos. Even consciousness, that most intimate mystery, might be tangled up with quantum vibrations humming inside our neurons. What's astonishing isn't just how bizarre these phenomena are, it's how they shape the universe we take for granted. Without quantum tunneling, stars wouldn't shine. Without the uncertainty principle, atoms would collapse. Dark matter, quantum biology, the arrow of time, each mystery is a thread in the tapestry, pulling at our understanding of existence. And the deeper we dig, the more we realize how much we don't know. The fine structure constants inexplicable precision, the simulation hypothesis uncanny plausibility, the Fermi paradox's eerie silence, all of them whisper that reality might be stranger than any fiction. So here's the ultimate question: are these mysteries roadblocks or are they signposts? Could solving them unravel the universe's deepest secrets, why there's something rather than nothing, how consciousness arises, whether we're alone in the cosmos? Or are they cosmic breadcrumbs leading us toward truths we're not yet equipped to grasp? The quantum realm doesn't just challenge our knowledge, it challenges our very notion of what's possible. And that's what makes it so thrilling. Now it's your turn. Which of these quantum enigmas keeps you up at night? Is it the spookiness of entanglement, the illusion of the holographic universe, or something else entirely? Drop your thoughts in the comments. Let's geek out over the cosmos' weirdest puzzles together. And if you're hungry for more deep dives into the edges of science, hit subscribe. Because the universe isn't done surprising us yet, not even close.